With this lecture, we're starting electric potential. Electric potential can be tricky for a few reasons. The first is that there's no mechanical counterpart. In mechanics, we learned about gravitational force, and then in this class, we learned about electric force, which was very similar. We learned about gravitational fields and how objects can exert forces on each other from a distance. And then we learned in this course about electric fields and objects exerting a force on each other from a distance through an electrical force. But there is no gravitational potential. This is a new idea, and it really is useful when we get to circuits. So unfortunately, we have to learn about potential first before we get to circuits, so we're not really seeing the cases where it's most useful yet. And there's no analogy in mechanics that helps us take this step into an electric potential. And then the other thing is that some of the underlying concepts are very simple, but students somehow want to memorize equations, which often works. But here, I think you'll be much better off if you don't try to memorize the equations and just try to understand why something has to be positive in this case, why it has to be negative there, why this would make sense or that would make sense. And electric potential is linked to work. So as long as you have a basic understanding of work from your mechanics class, you'll be okay here. And if you don't, we're going to do a quick review right now. So if you would take a moment and draw an object, let's just make it a box. Draw a force and a displacement vector on that object when the work done by the force is positive. I have an object, a box sitting on the floor maybe, and if I push on it with the force, and that box moves to the right and ends up over here, that force is doing positive work on the box. What if the force was doing no work on the box? Can you draw a situation with a force and a displacement where no work was done on the box? Again, I'll have my box sliding to the right. It ends up over here. But the force, maybe the force is coming from the floor, pushing straight up like a normal force. That force does no work on the box. And can you draw a situation where the work done by the force is negative? I'm going to use the same box, sliding in the same direction. It's going to end up over here. But this time my force is going to push in the other direction. So if you remember, work done is the integral of f dot dx. If the force is constant over that distance, it's just a dot product with the force and the displacement. A dot product means that the direction, the orientation between the force and the displacement matters here and determines the sign of the work done. It's the magnitude of the force times the magnitude of the displacement times the cosine of the angle you get when you put their tails together. Let's take a look at the first case. My force was in this direction. I'm going to put their tails together. My displacement is also in that direction. And so what angle do I get? 0 degrees. Cosine of 0 is 1. So the work is positive. It's just the magnitude of the force times the magnitude of the displacement. In my second case, the force points up at this angle, the displacement is to the right, and I get a 90-degree angle between them when I put their tails together. Cosine of 90 degrees is 0. So the work done in this case was 0. And if the angle is more than 90 degrees, like it is over here, the cosine is going to give us a negative number. Cosine of 180 is negative 1, so this one would be negative F delta x. Remember, if the force would cause the object to speed up, if the force increases its kinetic energy, like it would in the first case here, the force is pushing in the same direction it's moving, so it would cause the object to go faster and faster and faster. It would be doing positive work on the box. If the force does not affect the speed of the object, like in the second case, the force is perpendicular to the direction it's moving, it can't change the speed, it can only change the direction it's going. It does 0 work on the object. And if the force is slowing the object down, like in this last case, maybe that an example of that would be friction, right? You push a box this way across the floor, but the box slows down because friction is pushing back in the opposite direction. The box slows down. The force of friction would be doing negative work on the box. That was a quick review. Hopefully that all made sense. If not, go back and review work and dot products a little bit. One good habit to get into when you're talking about work done is always using this expression. Work done by some force on some object is whatever, positive, negative, 24 joules. So for example, I would say work done by friction on the box is negative 4 joules, something like that. Work done by the normal force on the box is 0. Work done by my hand on the box is positive. If you get used to saying it like that, it helps you with the work and linking it to an object, because work has to be done on an object. And if work is done on an object, that object's energy must change, because work is change in energy. Work done by some force on some object. Let's make sure you understand work by looking at a couple of quick examples. Here we have an object, my red dot, moving from point A to point B, while under the influence of two constant forces, F1 and F2, that are equal in magnitude. Is the total work done on our object by force F1 positive, negative, or 0? The work done by F1 on our object is negative, because our object is moving from A to B. It's moving in this direction, has a displacement in that direction. Our force, F1, is opposite that. If F1 was the only force acting on our object would be slowing down because of F1. It's doing negative work on our object. Or another way to think of it, there's a 180-degree angle between F1 and the displacement when we put their tails together. And the cosine of 180 gives us negative 1. So the work done is going to be F1 times delta x times the cosine of 180. Now, is the work done by F2 on our object positive, negative, or 0? Here the work done is positive. Our object is moving to the right. The force is to the right, and we have a cosine of 0 degrees, which is 1. in our formula for work. F times delta x times 1. Or another way to think of it is the force is pushing the same direction the box is moving. So if that was the only force acting on our object, the object would be going faster and faster and faster because of that force. Its energy would be increasing. The work done on our object because of F2 is positive. Now, is the net work done on our box positive, negative, or 0? The net work done is the sum of the work done on the box by F1 and F2. One is doing positive work, one is doing negative work, and they are equal in magnitude because the forces are the same and the displacement's the same. So the net work done is 0. The last question is the speed when the object gets to point B greater than, less than, or equal to the speed it had when it left point A. Because the work done is 0, we know the kinetic energy cannot change. The speed has to be the same. No net work was done on our object, so it has to have the same energy at point B that it had at point A. Let's do one more. We're moving our object from point A to point B under the influence of two forces. They are constant the whole time that the object is moving between points A and points B, but they're not equal in magnitude anymore. The force F3 is smaller than F4. The work done by F3 on our object is positive, negative, or 0. It's negative, as we discussed above. It points against the displacement. It would slow the object down as it moves to point B. How about F4? The work done by F4 on our object would be positive. And the net work done on our object? Positive, negative, or 0? Well, let's take a look at this. F3 is doing negative work. F4 is doing positive work. The distance is the same for both forces. F3 is being applied through a certain distance from A to B. F4 is being applied through the same distance from A to B, but F4 has a larger magnitude, so the work done by F4 is greater than the work done by F3. I should put absolute values around them. The magnitude of the work done by F4 is greater than that of F3. So that means that my net work done is positive. What can I say about the speed of the object at point B compared to the speed at point A? It has to be moving faster because positive work was done on our object. Its energy increased. One last topic with work is whether the force is conservative or non-conservative. Remember, for a conservative force, the work done from point A to point B was independent of the path taken. If I start here at point A and I end up here at point B, it doesn't matter if I take the straight line path or if I take this path or if I take this path. The work done is the same in every case. For a non-conservative force, that's not true. So think about friction. If we pushed a box across the floor from point A to point B, on those three paths, the work done by friction would be different for each of those paths. That's a non-conservative force. Which forces were conservative from our mechanics class? The gravitational force and the spring force. Every time we came up with a conservative force, there were only two in mechanics, gravitational force and spring force. Every time we had a conservative force, we came up with a potential energy term. right? Our spring potential energy term, our gravitational potential energy term. And now we're getting our third conservative force, the electric force. So we can come up with a potential energy for our electric force and use that in energy equations the same way we did when we had gravitational potential energy or spring potential energy. We can now have energy stored in our system because of electric charges interacting with each other.